Hello everyone, my name is Mohammed Karim Belaid, and I'm a master student at Porsche AG. Today, I'm excited to present the work that emerged from my master's thesis, conducted in collaboration with Passau University and Porsche. This project is a joint effort with Maximilian Rabus, a specialist in data science and digital transformation at Porsche, and supervised by Ralf Krestel from the Hasso-Plattner Institute at Potsdam University. Together, we developed CrashNet, an innovative encoder-decoder architecture designed to predict crash test outcomes. Let's dive into how this collaborative research evolved and the solutions we've developed for safer, smarter vehicle testing. At the passive safety department of a car manufacturer, we assess the safety of commercial cars using crash tests. These destructive tests are required by law in order to evaluate the safety of a car. Dummy shape and size differ. Here we see one male and one female dummy sitting in the front, while child dummies sit in the back. Using passive safety features such as airbags and seatbelts, car manufacturers try to mitigate the severity of a crash, in particular, trying to limit the chest acceleration of the occupant. Crash tests cover different scenarios. In this video, we see a front normal crash test, but there are also side impact crash tests, rollover, etc. It won't surprise you to learn that crash tests are expensive. For this reason, we demonstrate, in this paper, that we can predict the chest acceleration of the occupant during front normal crash tests using deep learning. This is the architecture of CrashNet. The model has two input flows. The first input consists of a list of scalars describing the crash scenario, like the initial car speed, the car mass, the dummy type, etc. The second input represents the car's acceleration. The output, or the target of the model, is the dummy's chest acceleration. Both time series consist of a 1D tensor, describing the changes in acceleration during the first 150 milliseconds of the crash. CrashNet's architecture consists of several layers, with CNN transpose layers as its core. The main features are shared CNN kernel weights and the use of deliberate bottlenecks. Let's start by analyzing the encoder part. The car acceleration is processed through multiple CNN and max pooling layers. In parallel, scalars are processed using dense layers. Now, the role of the decoder part is to learn 2D CNN kernels able to process time series and scalars simultaneously. Note that some cropping has been applied on the scalar's hidden state to avoid overfitting. Despite these bottlenecks, the scalars still have a high influence on the output. More details are provided in the paper. The output part is made of dense layers to learn time-related patterns as opposite to the encoder and decoder parts, which consist mainly of CNN layers. To evaluate CrashNet, we used a private dataset provided by Porsche. Crash tests are sensitive data and thus difficult to obtain. Moreover, some accelerometers might fail during a test. These failures result in a discontinued time series. We discarded incomplete time series, resulting in a dataset of 450 destructive crashes, plus 52 computer simulations. The 52 computer simulations represent very similar crash scenarios. They enable the model to learn how minor changes in the input affect the chest acceleration. We train models with and without simulation data to confirm the intended effect of this augmentation. We found out that the test error decreased by 3% and the quality of the predictions improved significantly. Since the dataset is relatively small, the choice of the test set has a high influence on the results. To mitigate this effect, we split the data using the five-fold cross-validation paradigm, which yields robust average scores. The validation set represents 41 random samples of the training set and is used to monitor the learning process. Let's analyze the quality of the predictions using the following example. Again, the car acceleration is the dotted line. The car touches the wall at t equals 0. Directly after, it starts decelerating. In contrast, the dummy inside the car keeps traveling to the front until it gets restrained by the seatbelt or the airbag. In this example, the dummy starts deceleration at t equals 60 milliseconds. CrashNet is able to capture this time-related effect and predict the chest acceleration curve with a tiny error rate. Moreover, the model is capable of capturing all kinds of diff shapes, especially the small waves, which are the hardest to predict. To conclude, there are different methods to assess the safety of a car. Each offers a specific advantage. Preparing a crash test takes about 5 weeks due to all necessary preparations. It can only be performed when the first prototype is ready, in other words, close to the production phase. Real crash tests are therefore expensive. The second solution is computer simulation based on finite elements method. Computing one simulation takes days of preparation to describe the entire car, plus 1 or 2 days for running the script using hundreds of cores. The final price is indeed cheaper compared to real crash tests, but it remains significant. Finally, we propose CrashNet, a new tool for car safety engineers, less demanding in terms of cost and preparation, and perfectly suitable for the early prototyping phase, where car description is not fully defined. Thank you for your attention.